We've spent a lot of time exploring the planets nearest to us. Mars and Venus are completely littered with dead robots at this point, and some living ones. However, what of the outer planets? Ignore Mercury, I want that thing disassembled for a Dyson swarm. Today, we're going to look into efforts to explore deep into our solar system, from the asteroid belt all the way out to the Oort cloud. However, bear in mind we'll be going chronologically, so we'll be jumping around the solar system a little bit. We also won't be covering missions to near-Earth asteroids such as OSIRIS-REx or the Hayabusa missions, although these definitely will merit a video of their own one day. With all the bandwidth and connection problems, deep space missions require very careful usage of data. That's something to really keep an eye on, data usage. Something you can make a lot easier by using today's video partner, NordVPN. Hey, now that's a segue. NordVPN is a leading provider in VPN services, which allows you to browse the web with more security and freedom than ever before. They believe in a free internet, the way it was truly envisioned when it was first made public to the world. Today's Wi-Fi networks can be compromised surprisingly easily by those with nefarious purposes you don't even want to start thinking about. And it gets even worse when you're using a public network like your local library or cafe. Nord allows you to encrypt your online traffic and keep it safe from those who would do you harm, but it doesn't stop there. It also has features to recognize malicious phishing attempts, those who pretend to be legitimate but are really just out there to take your data, and will warn you before you make that dangerous misclick. The Dark Web Monitor feature will keep an eye out for your credentials being displayed on underground hacker websites. For myself, I use Nord just to get American Netflix. I don't know if you know this, but Canadian Netflix isn't all that great, but Nord pays for itself entirely just by showing me all those shows I otherwise wouldn't have access to. But don't let that be the only reason. Visit nordvpn.com/dkis to learn why Nord is right for you and get started with a 2-year plan that includes 4 bonus months if you sign up using my link. Remember, that's nordvpn.com/dkis, or if you really want to spell it out, nordvpn.com/dkis today. Thank you, Nord, for making the internet more what it's supposed to be and for partnering with me for today's video. Now, speaking of the asteroids, let's start there. The earliest mission to pass through the asteroid belt into the outer solar system, which if you don't know is located between Mars and Jupiter, was Pioneer 10 in 1972, and encounters with asteroids were completely incidental, i.e. not really part of the planned mission. In fact, Pioneer 10 didn't really have a destination other than out, except for a pass by Jupiter, which we'll cover later. Before it did that, it became the first spacecraft to pass through the asteroid belt. Now, one thing to explain about the asteroid belt: Star Wars lied to you. Sci-fi movies feed us this expectation of areas with asteroids to just be littered with them, a dangerous path to traverse with giant rocks floating around in every direction, colliding and creating a complicated obstacle course to navigate. However, the truth is, if you were standing on the surface of an asteroid in the belt and you looked around, you most likely wouldn't be able to see any others with the naked eye. The average distance, between asteroids in the asteroid belt is around 965,000 kilometers, about 2.5 Earth-Moon gaps. So that being said, Pioneer 10 didn't exactly have to go through a shooting gallery on the way to Jupiter. Pioneer 10 and 11 were conceived as part of the Planetary Grand Tour, intending to visit every single outer planet, started in the early 1960s by NASA's Jet Propulsion Laboratory. Scientists noticed that in the late 1970s, a unique planetary alignment would occur that comes once every 175 years. This alignment would allow for an opportunity to make highly effective gravity assist maneuvers in which spacecraft could slingshot around planets on their way out of the solar system, accelerating them to their next destination without using too much extra propulsion. It would also allow multiple planets to be explored with a single spacecraft, a very cost-effective program, a good thing in the eyes of the post-Apollo world. While not the very first, Pioneer 10 was an early spacecraft to demonstrate the use of an RTG, or radioisotope thermoelectric generator, basically a nuclear battery fed by the heat given off by decaying plutonium, for power. Out beyond Mars, solar panels aren't very effective, unless you make them really, really big. We'll come back to that. So a good alternative is an RTG. These were kept on 2 10-foot-long trusses that stuck out from the hexagonal bus, which held propellant and the majority of instruments. The entire bus itself was kept within an aluminum honeycomb structure designed to keep it safe from micrometeoroid impacts on its long journey. Mylar and Kapton blankets provided passive thermal control, and 36 kilograms of hydrazine propellant was kept for attitude control with small thrusters. It carried instruments to measure planetary magnetic fields, detect particles of solar wind and cosmic rays, analyze radiation, detect micrometeoroids, detect helium and hydrogen in the Jovian atmosphere, and an imaging experiment intended to create an image of the planet out of dozens of small strips taken in red and blue light. Pioneer 10 was launched aboard an Atlas Centaur on March 3, 1972, and used a specially designed solid-fueled upper stage to accelerate it to a record speed of 51,682 kilometers an hour, the fastest man-made object at the time. It passed by the moon in just 11 hours, and over the course of 10 days, extended and activated all of its instruments as it prepared for a long journey. During that time, it became the first spacecraft to detect atoms of helium as well as aluminum and sodium within the solar wind, showing us that even in deep space, the vacuum isn't entirely empty. By July of 1972, Pioneer 10 had entered the asteroid belt, safely navigating through it with the closest approach to one being within 9 million kilometers of 307 Nike, a sizable asteroid discovered in 1891. However, it didn't collect any data on the asteroids, just got that record for being the first to fly by one. In November of 1973, Pioneer 10 gained a new record and finally arrived at Jupiter, becoming the first spacecraft to ever perform a successful mission to the gas giant. Over the course of 60 days, a series of 16,000 commands were sent to Pioneer 10 to control it and operate its instruments, beginning with an attempt to image the planet. By November 8th, the craft passed by the orbit of the outer moon Sinope, which at the time was simply known as Jupiter 9, not receiving its formal name until 2 years later. On November 16th, Pioneer entered Jupiter's bow shock. To explain, bow shocks for planets function similarly to that of a ship on the ocean. The planet is moving against the solar winds and cosmic gases in front of it, the relative speeds creating a high-pressure region or shock wave. Pioneer felt that it had entered the bow shock by detecting a drop in the solar wind by around 50%, from around 450 kilometers a second to 225 kilometers a second. The imaging efforts created over 500 images to transmit of varying quality, though many exceeded the clarity of any images ever taken from Earth. As it approached the planet, the radiation in the area got higher and higher, over 10 times stronger than the designers of the craft had predicted. As it passed through the inner radiation belts, it received integrated doses of 200,000 rads from electrons and 56,000 from protons. For reference, that's a little over 500 times more than a fatal dose for a human being, leading to fears that the spacecraft wasn't going to survive much longer. It continued to function, though the radiation did cause the generation of false commands, and while many were corrected, several images were lost as a result. Despite the difficulties, Pioneer 10 did successfully photograph Ganymede and Europa, though the latter was too distant for a detailed image. After passing within 132,000 kilometers of Jupiter's outer atmosphere, which was also roughly its maximum velocity, around 132,000 kilometers an hour, and obtaining close-up images of the planet's terminator and its iconic Great Red Spot, communications were lost as the planet blocked line of sight. Pioneer used this time to record detailed temperature data, creating an infrared map that confirmed Jupiter was radiating more heat than it was receiving from the Sun, something predicted but never confirmed up until this point. Pioneer 10 continued to take crescent images of the planet as it moved away, crossing the dynamic and ever-shifting boundary of the bow shock 17 times as it left Jupiter's influence. It was sent out into deep space, moving uninterrupted through the orbit of Saturn in 1976 and Uranus in 1979. That's right, that's how I'm going to say that planet's name, because I find those jokes to be the most dull, uninspired, copy-paste jokes in all of the space world. Wish to God we'd named it Eurectum. Pioneer 10 continued to transmit a weak signal all the way until 2003, though for the last 5 years or so, the signal contained next to no useful data, doing little more than confirming that the craft was indeed still alive. Its final very weak signal was received in January of 2003 at a distance of 12 billion kilometers from the Earth. Further attempts to contact it were unsuccessful, with NASA believing the RTGs no longer provide enough power to continue transmitting. However, as far as we know, Pioneer 10 continues to drift out of the solar system, derelict to this day. If ever found by some kind of intelligent life form, they will discover the Pioneer plaque, advocated for by Carl Sagan. Attached to the support struts of the antenna, the plaque shows an image of a male and female human being, as well as symbolic information regarding the location of the Earth and therefore the origin of the probe. Now, really quickly, 30 years doesn't seem like a very long time for an RTG-powered probe, does it? Well, it's not. The Snap 19 RTGs provide a combined 155 watts of power, which decayed to around 140 watts by the time it reached Jupiter. The half-life of the plutonium-238 used by the generators is around 87 years, meaning by the end of its lifetime, the power should have been around 80% of what it was at launch, about 124 watts. The spacecraft required 100 watts to operate all of its instruments, but by 2001, the total power output was only 65 watts. This didn't mean it was entirely inoperable, but it did mean that Mission Control had to pick and choose which instruments to use at any given time. Why was it so low? The thermocouple junctions deteriorated. Basically, the power generators were working fine, but the devices that transferred power from the generators to the instruments were not, eventually leading to Pioneer 10's early demise. Though it wasn't that early, it performed and completed its mission entirely according to plan. So, which probe was the second to enter deep space following Pioneer 10? Well, you're not going to believe this. Pioneer 11 was launched in April of 1973 and was structurally identical to Pioneer 10, but held some additional objectives. Originally launched on a direct intercept route with Jupiter, this was changed in 1974 after Pioneer 10 performed its flyby. With a 42-minute burn that used up 17 pounds of propellant, Pioneer 11 targeted a north-south flyby of Jupiter that would enable it to fly past a second planet, Saturn, in 1979. On its journey through deep space, Pioneer 11 had a handful of issues. One of its RTG booms initially failed to deploy, but succeeded after a second attempt. One of its attitude control thrusters also failed, which was an issue saved by NASA's standard redundancy protocols. There was a partial failure of an asteroidal dust detector, but throughout it all, nothing fully jeopardized the mission, and Pioneer 11 continued on its way. The probe's pass by Jupiter was much closer this time, coming within 42,000 kilometers of the cloud tops at its closest approach. It was also able to get the first detailed images of the Great Red Spot in the planet's polar regions, as well as use its instruments to determine the mass of the Galilean moon Callisto. It traveled much faster than Pioneer 10, 171,000 kilometers an hour at its fastest, as opposed to Pioneer 10's 132,000 kilometers an hour, meaning that even though it got much closer to the planet, it actually spent less time in the more dangerous zones of radiation. After repeatedly crossing the edge of Jupiter's bow shock just like its predecessor had, and taking over 200 images of Jupiter and its moon, Pioneer 11 left Jupiter in 1975, now headed for Saturn. 4 years later, in August of 1979, Pioneer 11 arrived at its next destination, becoming the first spacecraft to do so. A decision had been made to make it serve as something of a practice run for future missions, and its trajectory was altered slightly to have it pass through Saturn's ring plane to see if any small particles of the rings would damage it. None did, and by the end of August, Pioneer 11 began to pass through Saturn's bow shock, beginning thorough investigation of the planet and its moons. At one point, it took images of a minor moon that it then nearly collided with, coming within 4,000 kilometers of its surface. This small inner moon was tentatively identified as Epimetheus, but it could have been Janus, as the two are in very similar orbits. It continued inward towards Saturn, measuring the planet's magnetic fields, doing a flyby of the moon Mimas, and I'm not making that joke because it's been made about 1 billion times, and a flyby of Titan, during which it concluded that Titan is far too cold to support life. Not exactly an unexpected conclusion. Pioneer 11 also got quite close to Saturn, coming within 21,000 kilometers of it, and now moving at a speed of 114,000 kilometers at its closest approach. In addition to the data it was intended to provide, the craft also discovered a new ring around the planet, named the F-ring. The F-ring is the outermost ring layer, and is very faint, invisible from the Earth without the use of something very powerful like the Hubble Space Telescope. Temperature readings recorded Saturn as being around negative 180 degrees Celsius, and photographs of the cloud layers confirmed that it was far less diverse in terms of visual features compared to Jupiter, with a likely composition of primarily liquid hydrogen. After concluding investigation of Saturn, Pioneer 11 was flung out of the solar system in the opposite direction as its predecessor, heading roughly for the center of the Milky Way galaxy. By 1990, it had passed the orbit of the planets and was headed for the edge of the solar system. However, by 1995, the power had degraded to a point where it no longer responded to commands, and its last signal was received on February 24, 1995. Now, before we move on from the extreme success of the Pioneer probes, we need to discuss an anomaly.
We have had an anomaly?
No, not that kind of anomaly. The Pioneer anomaly. After Pioneer 10 had passed by Jupiter, and after Pioneer 11 had passed by Jupiter and Saturn, their trajectories deviated from what was expected. More specifically, they were slowing down more than they should have, and nobody could figure out why. The initial attempted explanation was that the starting conditions had simply been calculated wrong, or perhaps it was due to a poor understanding of gravitational or drag forces on objects in deep space. However, by the late 1990s, a more likely theory had been developed, and with the analyzing of data from other similar spacecraft, this theory was more or less confirmed by the 2000s. It was the RTGs. RTGs produce power by radiating thermal energy, and that energy has to, well, radiate. This creates a very small but consistent propulsion force, and depending on which direction the spacecraft is oriented, this force could be pushing in the opposite direction of motion. Furthermore, this explained why the deceleration wasn't consistent. The spacecraft was slowly tumbling through space, and eventually the radiative force would be facing in the direction of motion or in some other negligible direction rather than retrograde. It was a mystery that plagued engineers and physicists for decades, but it's rather amusing to know that the cause was its own source of power. The Voyager program was conceived as part of the Planetary Grand Tour, utilizing a pair of spacecraft originally intended to be Mariner 11 and 12. Mariner 10 had, in 1973, demonstrated the efficacy of gravity assist maneuvers to explore multiple planets when it passed by both Mercury and Venus, and the next pair of spacecraft intended to expand this during the rare planetary alignment opportunity ahead of them. Over time, their designs deviated so much from the rest of the Mariner program that NASA announced a competition to rename the spacecraft in 1977. Eventually settling on Voyager, the two probes were launched out of numerical order, with Voyager 1 following the Jupiter-Saturn path of Pioneer 11, and Voyager 2 doing the same before then going on to pass by Uranus and Neptune. The identical Voyager probes sit on a hexagonal bus, perhaps the only Mariner-derived part at the tail end of their design, on which 105 kilograms of scientific instruments are mounted. The 3.7 meter wide high-gain antenna is on the top of the bus, and extending out from the spacecraft are 3 booms. One boom holds the 2 low-field magnetometers at the far end, with a high-field magnetometer closer to the bus. Another boom holds the majority of the other instruments, including an imaging system, a radio science system to determine the properties of planets, an infrared interferometer, spectrometer, and radiometer, say that 5 times fast, which investigate the local energy balance and atmospheric conditions, an ultraviolet spectrometer to do the same, as well as measure radiation, a cosmic ray detector, a charged particle instrument, and a plasma spectrometer. Did I get all of it? I think I did. The Voyager probes were really packed with science, and what's wild is that these probes were scaled down from initial designs to compensate for budget allocation that was lost to the then in-development shuttle program. Oh right, the third boom. That one was for power, holding 3 specially designed MHW RTGs, providing approximately 470 watts at launch. Perhaps the most well-known aspect of the Voyager probes is the golden record attached to the bus of each spacecraft. They serve as a kind of time capsule, intending to communicate with any extraterrestrials who might encounter them in the future. Their contents were chosen by a committee chaired by Carl Sagan at Cornell University and consist of 116 images, a variety of natural sounds such as wind, thunder, and animals, spoken greetings in 55 languages, and musical selections from different cultures and eras. The visual data is reconstructed via raster scan, which scans individual lines and reconstructs them in a rectangular pattern. The audio data is played via phonograph, and the cover of the record depicts how to construct and play one. In addition, the cover also shows a pulsar map and a hydrogen molecule. Previously, NASA had received public criticism for displaying images of a naked man and woman on the Pioneer plaque, and so these were omitted for Voyager, though silhouette versions are still contained on the record data. If you're curious how I personally feel about this controversy, note that I chose not to censor the Pioneer plaque. Since it covers familiar territory, we'll cover Voyager 1 first, even though it launched second. It was sent up on a Titan IIIe on September 5, 1977, and since I'm not sure which Voyager launch this occurred during, I might as well mention it now. On the BBC television series Connections, James Burke was at KSC describing how rockets work and had one opportunity to time this shot perfectly. Let's see if the BBC will allow me to play it.
You get?
Damn. Well, I tried. I always found it funny that he spends all of that time describing the chemistry of a liquid-fueled rocket launch and then proceeds to point at a rocket which has just lit solid-fueled engines. It does have a liquid stage in the middle, but that doesn't ignite until mid-flight. A further fun fact, the launch nearly failed. The Titan's second stage shut down prematurely, leaving over 500 kilograms of its propellant unused. Thankfully, the Centaur upper stage was able to compensate for this, just barely. At the end of its extended burn, it had approximately 3 seconds of fuel left. Not something it could have done successfully on Voyager 2. By the end of the year, somewhere in the asteroid belt, Voyager 1 overtook its sister spacecraft due to its path being more direct toward Jupiter. It arrived at the gas giant in January of 1979, beginning photography and creating this beautiful series of images upon approach. It discovered active volcanism on the moon of Io, the first time such activity had been seen on another planet. It was also noted that large amounts of sulfur, oxygen, and sodium pervade the magnetosphere of Jupiter, and this most likely originated from Io, flung into the surrounding space both by eruptions and by impacts to the surface. Enough data on Io and the materials in its orbit were collected to conclude that in the 4.5 years since Pioneer 10 and Pioneer 11, something had changed. It seems highly unlikely that Io's volcanoes were not active only half a decade earlier, yet it also seems unlikely that both Pioneer instruments failed to detect any of this activity. However, perhaps it's not too difficult to believe this later point, given that both of them also failed to detect or see Jupiter's ring system. They both knew that they were there, inferred from observation of the planet's radiation belts, but never directly imaged until Voyager. We tend to forget that Saturn isn't the only ringed planet in our solar system. In fact, all 4 giant planets have them. Jupiter has 4 main rings, a thick inner torus known as the halo ring, a bright but thin main ring, and 2 wide, thick, but very faint gossamer rings. Voyager 1 took the first ever image of the ring system, a single overexposed photo that finally confirmed that they were there. 1 year later, Voyager 1 arrived at Saturn, with its closest approach of 124,000 kilometers occurring in November of 1980. Its cameras detected complex structures within Saturn's rings, its instruments measured its upper atmosphere to be around 7% helium and almost all of the rest being hydrogen. It was expected to have around the same amount of helium as Jupiter, around 11%, but with it being much lower, some theorized that the helium in the upper atmosphere was slowly sinking through the hydrogen, creating some of the excess heat that Saturn radiates. The winds of the planet were measured, finding that they blow about 500 meters per second in a mostly easterly direction, and that the planet itself rotates at a rate of once every 10 hours and 39 minutes. After Pioneer 11 concluded the atmosphere of Titan to be very thick and complex, Voyager 1 was sent on another flyby. It passed within 6,400 kilometers of the Moon, determining the composition, density, and pressure of the atmosphere, and measuring its mass based on its effect on the probe's trajectory. The hazy atmosphere is far too thick to see through, but all of the measurements did lead to speculation of liquid hydrocarbon lakes on Titan's surface, something we now know more or less for sure. By 1990, Voyager 1 was far enough away to take the first family portrait of the solar system, a collection of 60 photos showing 6 planets in a partial background to indicate their relative positions from a distance of approximately 6 billion kilometers away from the Earth. One of these photos is the famous pale blue dot, popularized by Carl Sagan, who wrote extensively about its symbolism of showing humanity's minuscule place in the cosmos. I won't quote the whole thing, but I'll give you my own personal summary. It is interesting to note that over hundreds of thousands of years of evolution, of conflicts and progress and upheaval and triumph, everything humanity has ever done, ever achieved, or created or destroyed, all of it has occurred right there, on a dot less than a pixel wide, lit up by a sunbeam billions of miles away from the camera that took the photo. A pale blue dot suspended in a sunbeam. That's us. All of us. For the time being. In 2003, Voyager 1 entered the termination shock. This is the point where solar winds slow to subsonic speeds due to interactions with the local interstellar medium. The thing is, we often describe the Voyager probes as, quote, leaving the solar system, and they are, but it isn't exactly a solid boundary. Beyond the termination shock, solar wind is slowed further, compressed and made turbulent within a layer called the heliosheath. Theoretically, beyond the heliosheath is the heliopause, where solar winds are stopped entirely by the winds of the surrounding stars. As of 2012, Voyager 1 was believed to be approaching the heliopause, indicated by a rapid increase in cosmic rays and a drop in protons from the Sun at a distance of around 121 AU from the Sun, AU being astronomical unit, which was defined as 1 Earth-Sun distance, but is now defined as 149,597,870.7 kilometers exactly. At this point, it is generally accepted that Voyager 1 is fully within the interstellar medium, though this isn't exactly the same as leaving the solar system, as the solar system typically includes an area called the Oort cloud, a massive region of icy planet-like objects believed to be the source of long-period comets that enter the solar system. In recent years, Voyager 1 has been suffering serious communications issues, sending back garbage data through a computer that was no longer functional, corrupting the data. Numerous attempts have been made to fix these issues, switching computers, rebooting computers, routing through different computers, but over time, the spacecraft is gradually becoming unusable. Its total memory of 69.63 kilobytes has been a major limiting factor, with engineers deleting unused code to save space, such as the code used to transmit data from Jupiter. Engineers have continued to switch off instruments throughout time, and by 2036, it will be entirely out of range of the Deep Space Network, making communication fully impossible. Regardless, it will continue on its way out of the solar system, the furthest man has ever reached into deep space. Voyager 2 passed by Jupiter in the same year as its sister probe. It focused heavily on confirming the earlier volcanic observations on Io, and together, Voyager 1 and 2 directly observed 9 different eruptions from the Moon's surface, with evidence that other eruptions occurred during this time but were not directly seen. Plumes from the volcano stretched out 300 kilometers in altitude, and material objective was observed moving in the ranges of kilometers per second. Voyager 2 also deepened the mystery of Europa. Voyager 1 provided some low-resolution images that showed curious topographical features, initially believed to be cracks in the Moon's crust caused by tidal forces. However, higher quality images from Voyager 2 only made everyone more confused, as the lines on the surface appeared to lack any topographical relief, which is to say, they lacked depth. They didn't seem like canyons or deep rifts, and in fact one scientist said they looked as though they had been, quote, painted on with a felt marker. For the time being, they simply didn't know what had produced these lines. Nowadays, the most likely hypothesis is that the lines on Europa were produced by a series of eruptions of warm ice, as Europa's crust slowly spreads open to expose warmer layers beneath. By 1981, Voyager 2 arrived at Saturn. Its primary goal here was to use its radio link to examine Saturn's upper atmosphere while the planet passed between itself and the Earth. In the highest layers of the atmosphere, where the pressure was only around 1 psi, the temperature was recorded as being around negative 191 Celsius. Deeper down, the temperature rose to around negative 131 Celsius, but the pressure steeply increased to around 17 psi. This was also the first observation of Saturn's hexagon, a persistent cloud pattern around the North Pole with somewhat mysterious origins even to this day. Other observations of Saturn by Voyager 2 included the discovery of new satellites within the ring system, initially inferred through disturbances in the rings themselves. It also observed several small gaps in the ring system that initially went unnoticed. However, at the same time, some of the Saturn observation was marred by a mechanical problem. One of the actuators on the scan platform seized up, which caused the loss of some imaging opportunities on its way out of the Saturn system. Over time, however, as it headed to its next destination, engineers were able to issue a series of commands that eventually gave the scan platform the majority of its function back, resuming normal operations well before it arrived at Uranus in 1986. This far out from the Earth, there's little that can be determined about Uranus without simply going there, so Voyager 2 presented a unique opportunity for study of the ice giant. We knew about its unusual axial tilt of 82 degrees, putting it roughly on its side when compared with the rest of the solar system. This was mainly through observation of its poles as they move from one side to the other from our point of view, as well as through observations of its rings, which are aligned with its equatorial plane. The rings were discovered in 1977, not through direct observation, but by observing a star that Uranus was passing in front of, noting that the star dimmed twice on either side of the planet. As Voyager 2 approached, 11 new satellites circling Uranus were observed, its 17-hour rotation period was discovered, and false color images revealed distinct bands in its thick cloud layers near the South Pole. Within these poles, the probe recorded 140 flashes of lightning, though these were not recorded in the visible spectrum. While we did know that the ring system existed, Voyager 2 was able to observe and confirm 2 new layers to the rings, and provided evidence that suggested that, unlike Jupiter and Saturn, Uranus's rings were not formed at the same time as the planet, instead being a result of a satellite that was ripped apart by tidal forces relatively recently. The next year, Voyager 2 arrived at Neptune, and to this day is the only spacecraft to directly explore the 2 ice giants. A course correction on the way put it on a proper flyby route that took it over Neptune's North Pole at an altitude of just under 5,000 kilometers. It was again able to record lightning flashes in the ammonia clouds of the upper atmosphere, discovered the planet's thin ring system, and confirmed 6 new moons. It also observed what was called a Great Dark Spot, which was later found to disappear in observations from the Hubble Space Telescope, and is hypothesized to have been a clear region of gas that provided a brief window through the planet's thick methane cloud layer. 5 hours after its Neptune flyby, Voyager 2 flew past Triton, the planet's largest moon. This served to debunk several theories about the moon, including that of a thick atmosphere. It turns out Triton's mostly nitrogen atmosphere is quite thin and somewhat variable over the course of its orbit. Following this flyby, Voyager joined its sister probe on an extended interstellar mission out of the solar system, which it continues to this day, having overtaken Pioneer 10 just 2 years ago. The 2 Voyager probes remain the most distant man-made objects in existence, and though both barely work anymore, they represent the furthest extent of our reach into the cosmos. The next probe to explore deep space, oddly enough, was not designed to explore an outer planet, but rather the Sun. A collaboration between NASA and ESA, the European Space Agency, the Ulysses spacecraft was launched in 1990 aboard Space Shuttle Discovery. It was intended to explore the Sun from high latitudes, as previous spacecraft and ground observations only did so from relatively close to the star's equatorial plane. It had a roughly box-shaped body, upon which the high-gain antenna, a new general-purpose RTG, a radio plasma antenna, and a magnetometer boom were mounted. It utilized extensive blanketing and electric heaters, both to protect it against the cold during a planned Jupiter flyby, and to protect it from the heat of the inner solar system. Within the box-shaped probe bus was the rest of the instruments, primarily for detecting various solar particles, interstellar dust, and solar winds. Originally intended to be launched via the shuttle Centaur upper stage, this plan was scrapped following the Challenger disaster in 1986. It instead used 2 upper stages, both solid-fueled, the inertial upper stage and then a payload assist module, both previously used to launch other satellites via the shuttle. These two combined set it on a path toward Jupiter, which it swung by in 1992 to send it up the elliptical plane by about 80 degrees, making it able to observe the poles of the Sun. Unfortunately, as its primary goal was just a gravity assist maneuver, only a small amount of study of the planet's magnetosphere was performed. It was then flung off the equatorial plane to allow it to directly observe the Sun's high latitudes, which took place between 1994 and 1995. Ulysses did a lot of work to further refine our understanding of the Sun. Data show that there is a weakening of the solar wind over time, which was at a 50-year low in 2008, that the solar magnetic field at the poles is much weaker than previously assumed, that the Sun's magnetic field reverses in direction every 11 years, and more. It even discovered that small dust particles coming in from deep space into the solar system are 30 times more abundant than previously assumed. Following its study of the Sun, Ulysses was given an extended mission, the study of comets. In 1996, the probe unintentionally crossed the path of the comet Hyakutake, measuring its tail to be almost 4 astronomical units in length, which, by the way, is huge. In 2004, the material from a second comet's tail was ejected by a coronal mass ejection toward the probe, allowing further study. Finally, in 2007, it passed through the tail of Comet McNaught, the results of which were surprisingly different from the first tail pass, and it was able to measure a drop in the solar wind velocity by around 300 kilometers per second. Ulysses had its mission extended yet again to allow for a second study of the Sun through 2007 and 2008. By this point, power from the RTG had deteriorated somewhat, making it unable to power all the heaters at once. At this point, instrument power sharing was started, turning off some instruments in order to keep the heaters powered, then turning off all the heaters once it got closer to the Sun. Then, finally, after operating for 4 times longer than intended, the end of the Ulysses mission was announced on July 1, 2008. It was no longer able to keep its hydrazine fuel from freezing, meaning it could no longer orient itself and couldn't keep its instruments pointed in the right direction or its antenna. It remains in orbit of the Sun, and likely will forever, unless another chance encounter with Jupiter sends it slingshotting out of the solar system to join the Pioneer and Voyager probes. Speaking of Jupiter, that's where we return to after Ulysses, this time for a much longer duration. The Galileo spacecraft was again based on the design of the Mariner probes, but had a fairly lengthy development process, leading to a final design so far removed from Mariner that it required a new name. John R. Cassini, who had headed both the Mariner and the Voyager projects, solicited suggestions, and most votes went to name it after the man who had first viewed Jupiter through a telescope, Galileo Galilei, formally adopted in 1978. Galileo had one rather unique aspect to its design. Most spacecraft are stabilized by one of two means. Either it spins around a fixed axis, or it maintains a fixed orientation with reference to the Sun and a star. Galileo, however, did both. One section of the craft rotated at a speed of around 3 revolutions per minute, while another was stabilized with star trackers. The spinning section held 6 instruments that gathered data from many different directions, specifically the fields and particles instruments. In addition to being the first Jovian probe to have its own propulsion, which allowed it to enter orbit of Jupiter, it had another piece of first-time space technology, an atmospheric entry probe. Built by the Hughes Aircraft Company, the probe was contained in an aeroshell and heat shield of the same material originally developed for rocket nozzle throat material, carbon phenolic. The strength of the heat shield was tested in an all-new laboratory purpose-built for this testing, the Giant Planet facility. It featured a suite of instruments for measuring pressure, atmospheric and gas composition, cloud particle observations, measuring wind speeds, and light and radio emissions. Galileo was launched aboard Space Shuttle Atlantis in October of 1989, using an inertial upper stage to send it on a rather roundabout path to Jupiter. On its way, it became the first spacecraft to do close flybys of asteroids within the asteroid belt. First, it came within 1,700 kilometers of 951 Gaspra in 1991, determining it to be rich in olivine and pyroxene. It also noted that there is very little albedo, or differences in color across the terrain, and a lack of large impact craters led many to believe it is a relatively young asteroid, having broken off from its parent object around 200 million years ago. Using an optical navigation camera to determine exactly where the asteroid was, Galileo was oriented carefully during its approach and took 57 images as it passed by, capturing the odd tumbling rotation of this oblong object. 2 years after launch, Galileo doubled back from the asteroid belt back to Earth, performing a second gravity assist maneuver to gather enough speed to send it all the way to Jupiter. On its second pass through the asteroid belt, it had another close encounter, this time with 243 Ida, which was discovered to have a very small moon of its own named Dactyl. This was the first time it was ever discovered that an asteroid could maintain a satellite of its own. Galileo had one more chance encounter before it arrived at Jupiter, this time with a comet. In 1993, it was discovered that comet Shoemaker-Levy 9 had entered Jupiter's Roche limit, basically the point at which an orbiting object will begin to be torn apart by tidal forces. It was predicted that the comet's fragments would soon directly collide with Jupiter, and while Galileo was still over 200 million kilometers away, Jupiter was 66 pixels wide in its camera, and a unique opportunity was presented. The pieces were observed smashing into the planet at over 300,000 kilometers an hour, leaving brownish impact sites several times larger than the Earth that persisted for weeks and creating waves that rippled through the clouds for hours. On its way to Jupiter, Galileo's high-gain antenna was finally deployed, only there was a problem. It didn't deploy the whole way. It had 18 graphite epoxy ribs that were driven by motors that put pressure on them to deploy the antenna. The process was supposed to take 165 seconds, however, telemetry showed that the motors had stalled after 56 seconds. 15 of the 18 ribs had popped out, and it was impossible to reverse the process and try it again. They tried several fixes. One was to move the spacecraft toward and away from the sun, hoping that heating and cooling the ribs might expand and contract them enough to make them pop out, but this didn't work. They also tried swinging the low-gain antenna into a hard stop, effectively shaking the entire spacecraft to loosen the ribs, but this also didn't work. Pulsing the motors was also tried in another effort to shake the antenna loose, but over a 3-week period, they only managed to move a stalled ball screw 1.5 revolutions beyond where it had stopped. Now, here's the worst part. This is yet another problem that, effectively, can be blamed on the Challenger disaster. Following the grounding of the shuttle fleet and the reorganizing of the probe's deployment, Galileo was placed into storage for 4.5 years. During this time, the lubricants between the tips of the ribs eroded away and then were worn down further by the cross-country journeys by truck from California to Florida. Another cost-saving measure, these truck journeys vibrated the spacecraft, and the ribs that failed were those closest to the flatbed trailers. A decision made in order to save about $130,000 permanently crippled Galileo's high-gain antenna. This didn't completely ruin the mission, however. The 2 low-gain antennas were capable of transmitting back all data, just at a severely reduced bandwidth. Instead of doing it at 134 kilobits per second, it was limited to a shockingly slow 8 to 16 bits per second, which also required a series of software changes to be uploaded to the spacecraft. Galileo finally arrived at Jupiter in December of 1995, much later than it would have if the more powerful Shuttle Centaur upper stage had been available. It had deployed its atmospheric probe about 5 months earlier, which freed up its propulsion system and allowed the orbiter to move off of a collision course with the planet. After a gravity assist from Io, the probe entered orbit of Jupiter in such a manner that it could effectively tour the Galilean moons while it circled the planet. Over the course of its mission, it had 4 close encounters with Ganymede, 3 with Europa, and 3 with Callisto. It stayed away from Io outside of its initial encounter out of fears that the high radiation would damage instruments and prematurely end the mission. The atmospheric probe surprised everyone. It was expected that it would fall through 3 layers of clouds, a top layer of ammonia ice particles, a middle layer of ammonium hydrosulfide, and a third layer of water vapor. However, it only found one significant cloud layer, which it descended through at a breakneck speed of around 170,000 kilometers an hour. It decelerated at an unprecedented 228 Gs, and the heat shield lost more than half of its mass during this time. It deployed its parachute very late, then dropped its heat shield, continuing to transmit data until it was around 180 kilometers below the tops of the clouds. Here, the temperature increased to over 1,700 degrees Celsius and the pressure to over 70,000 psi, which easily destroyed it. During its descent, it found far less lightning and water than expected, but the winds were much stronger at around 350 kilometers an hour, with gusts of over 500 kilometers an hour. Early in the orbiter's mission, tape recorder problems prevented the imaging of Io and Europa, focusing instead on the field and particles instruments. Throughout the life of the orbiter, these problems put a significant cap on how much data could be stored and transmitted at one time. However, the mission was still considered an extreme success, collecting a massive amount of data on Jupiter and its moons. One could almost make an entire video just about the results of the Galileo mission, and one day I probably will, but I'll highlight a few details. Europa, for instance, was found to have very few impact craters. Since it seems unlikely that it somehow avoided the intense bombardments that the Jovian system is subjected to, it is instead believed that Europa has a very active geology, which continuously renews the surface topology and erases craters from existence. This surface renewal also gave further credence to the currently believed theory that Europa has liquid subsurface oceans kept warm by geothermal vents. The moon of Ganymede was found to have a substantial magnetic field, the first natural satellite to be known to have one. The rings of Jupiter are now, thanks to data from Galileo, believed to have been formed by dust kicked up by interplanetary meteoroids that strike the 4 innermost moons. In 2003, the Galileo project was formally concluded, and the final fate of the orbiter was decided. Since the Surveyor lunar probes in the 1960s were found to have brought Earth-borne bacteria to the moon, interplanetary contamination became a serious concern. Galileo had not been properly sterilized before launch, and so the decision was made to crash it directly into Jupiter to avoid contaminating the moons with an accidental collision, particularly Europa. On September 21, 2003, Galileo collided with Jupiter on its dark side at a speed of around 48 kilometers per second. Cassini-Huygens, which will henceforth simply be called Cassini for the sake of my sanity, was the next mission headed for Saturn. A collaboration between NASA, ESA, and the ISA, which is the Italian space agency, it consisted of two parts, an orbiter and ESA's Huygens lander aimed at the moon of Titan. The orbiter was yet another Mariner-derived design, starting to see a pattern there, and held a suite of optical remote sensing instruments, fields, particles, and waves instruments, and microwave remote sensing instruments. The Huygens lander was a simple disc-shaped device that would land with the assistance of a heat shield and a parachute, and was tended to be robust enough to survive any landing at any site, be it a flat plain, a mountain range, an ocean, or something else. It housed sensors to measure the structure and properties of Titan's atmosphere, measure the wind speeds, a descent imager, a spectral radiometer, two gas sensing instruments, and a science package for determining the properties on the surface of the impact site. Cassini was launched on a Titan 4B Centaur in October of 1997, once again taking a roundabout route to its destination. It first performed 2 flybys of Venus, returned to Earth in 1999 for another gravity assist, and then out into the asteroid belt. It passed by 2685 Masursky, an asteroid in the central belt, though it didn't get very close, then was flung past Jupiter in late 2000. This process took 6 months, allowing it to take around 26,000 images of Jupiter, its rings, and its moons, producing some of the most detailed results to date, showing details that are only around 60 kilometers across. A major finding of the flyby regarded the circulation of Jupiter's atmosphere. Previously, dark belts alternating with light zones in the atmosphere were considered to be upwelling air, similar to how clouds form on Earth when air is rising. However, Cassini found that the upwelling bright white clouds also pop up in the dark belts, leading researchers to believe that the dark areas are simply the result of Jupiter's net rising atmospheric motion throughout its year, so to speak. While between Jupiter and Saturn, Cassini performed tests of Einstein's theory of general relativity, which states that a massive object like the Sun should cause space-time to curve. The mission team performed specific radio wave activities at a time when those waves would pass close to the Sun, which should create deviations in the radio frequencies, and they did, within agreement of the calculated values of 1 part in 1,000, firmly supporting the theory of general relativity. After a 7-year voyage, Cassini finally entered orbit of Saturn in July of 2004, after passing through a gap in 2 of the planet's rings. It performed several flybys of Titan, and in December of 2004, released the Huygens lander toward it. The probe made a 2.5-hour descent through Titan's thick atmosphere, eventually coming to rest on what is believed to be a shoreline, bouncing onto a flat surface, then sliding a little before finally coming to rest. Images returned showed a flat plain covered in pebbles, believed to be made of hydrocarbon-coated water ice. The temperature was around 179 degrees Celsius, and the surface pressure was just under 1.5 atmospheres. Around 90 minutes after landing, the Cassini orbiter passed out of range and turned its antenna away, effectively ending the mission of the Huygens lander. Over the next several years, Cassini would extensively study Saturn's rings, its major moons, the lakes of Titan, a hurricane at Saturn's south pole with a distinct eye wall, the first such storm ever found on another planet, and more. In 2008, Cassini's mission was extended with more flybys of Titan, Enceladus, Mimas, and Tethys. It was again extended in 2010 until 2017, conducting 54 more Titan flybys and 11 more of Enceladus. In October 2012, Cassini was able to see the aftermath of the Great White Spot, a storm that occurs roughly every 30 years and is visible through a telescope. Cassini noted a huge increase in ethylene gas believed to be related to the iconic white clouds produced by the storm. Between 2012 and 2016, Saturn's hexagon changed color. Images from Cassini noted that the once mostly blue cloud pattern had become more golden, believed to possibly be related to a seasonal change, as there was also less blue color between 2004 and 2008. Amidst a turbulence of government funding drama, Cassini performed what was called its grand finale starting in 2016, which gradually changed its orbit by having it fly continuously between Saturn's rings, allowing it to better view Saturn's hexagon, and then finally, on September 15, 2017, plunged into Saturn's atmosphere and formally ended the mission. Over the course of its journey, over 635 gigabytes of data were returned to Earth, 6 moons were discovered, and almost 4,000 scientific papers were published. In 2006, the New Horizons probe was launched, intending to be the first probe to perform a flyby of Pluto, with an extended mission to study the icy Kuiper Belt objects beyond it. Taking inspiration from the Ulysses probe, it has a triangular body with its RTG power source extending from one side, actually a spare RTG from the Cassini mission. It utilizes a powerful long-range reconnaissance imager, a solar wind analyzer, an ion and electron sensor, an ultraviolet imaging spectrometer, a 75mm telescope, a dust counter, and a radio science experiment. New Horizons was launched on an Atlas V in 2006 after several delays, and the injection burn of the ATK Star 48B upper stage took it out of the Earth-Moon system so fast that it passed by the Moon in only 9 hours. In the next year, it flew past Jupiter, though its primary objectives overrode doing much study of it. Its necessary path kept it millions of kilometers away from the Galilean moons. However, its instruments were specifically designed for small, dim targets, so it was still able to image all 4 of the moons in relatively high quality, even capturing volcanic eruptions from the surface of Io. New Horizons spent most of its journey toward Pluto snoozing. Hibernation mode shut down redundant control systems to increase their lifetime, decrease operating costs, and free up the deep space network. Every now and then, the probe would speak back to Earth, letting everyone know that it was still operating normally, assuming that it was. For about 2 months out of every year, it would be woken up, calibrated and checked, then returned to hibernation mode. On December 6, 2014, it was finally fully awakened to prepare for its Pluto encounter, beginning distant encounter operations in January of 2015. While it was approaching, investigators compiled a list of Kuiper objects for its second target, and at the same time, New Horizons suffered a software glitch and went into an emergency safe mode. Its mission was paused until it could be figured out. Thankfully, within 3 days, the team had in fact figured it out. A timing flaw in a command sequence had caused the glitch. Basically, New Horizons was told to do 2 things at once, and it was rectified without any major losses to science observations. The closest approach to Pluto occurred on July 14, 2014, at a distance of around 12,000 kilometers. Telemetry data confirmed that the flyby had occurred, but due to its instruments being pointed towards Pluto, everyone had to wait for the actual data to be returned. The complete dataset was returned over a course of 15 months at a rate of around 2 kilobits per second. The flyby was a complete success, characterizing Pluto and its moon Charon's geology and morphology, mapping chemical compositions, and characterizing the tenuous atmosphere of the planet. It was able to image all 5 of Pluto's known satellites, characterize surface temperatures, ionosphere, and map the terminators of both Pluto and Charon in high resolution. On August 28, 2015, New Horizons' target in the Kuiper Belt was chosen, 486958 Akaroth. Catchy name, right? It made a course correction in October, and the flyby occurred in January of 2019. Akaroth, I'm not repeating the numbers every time, screw you, is a rather unique-looking cosmic object, being a contact binary, 2 objects that had gravitated toward one another and essentially fused together, creating its peanut-like shape. Again, due to the low bitrate and the vast distance, New Horizons took its time returning data, showing the mapped surface geology, surface temperature, and signs of any satellites or rings over a period of around 20 months. Today, New Horizons is continuing into deep space, having been used to take images of Proxima Centauri to show stellar parallax between itself and the Earth. It remains healthy and fully functional, currently at a distance of around 61 astronomical units from the Earth. Commands sent to it have a 16-hour round trip at the speed of light. The most recent trip to the outer planets, that has actually reached this objective, is Juno. Juno is the first outer probe to be powered by solar arrays, utilizing the 3 largest solar panel wings ever developed at the time in order to gather sufficient power from the Sun at such a vast distance. Juno is the second probe in the New Frontiers program, the first being New Horizons, and the second probe to orbit Jupiter, having arrived there in 2016, 5 years after its 2011 launch. Hosting a magnetometer, a microwave radiometer, an infrared auroral mapper, a gravity science experiment, an energy particle detector, a radio and plasma wave sensor, an ultraviolet spectrograph, and finally a visible light camera and telescope, Juno was launched aboard an Atlas V into an elliptical heliocentric orbit, returned to Earth, and used it to slingshot around toward the Jovian system. It performed an insertion burn on July 5, 2016, entering an elliptical orbit of Jupiter. It is currently performing its 3rd extended mission that will last until September of 2025, at which point it will be deorbited into Jupiter's atmosphere. Juno has made a number of discoveries currently challenging existing theories about Jupiter, including the solidity of its core, which may not be so solid after all. Juno has also produced some of the most beautiful images of Jupiter to date, and I'd just like to take a moment to pause and appreciate some of these. Do note that many of these use false color or are otherwise enhanced to show variations in chemical composition or cloud heights. There are currently 3 deep space missions that have been launched but not yet reached their objectives. The first is Lucy, which is slated to visit 2 asteroids in the main belt, and 6 Jupiter Trojans, which are asteroids that share roughly the same orbit as Jupiter around the Sun. The second is JUICE, or the Jupiter Icy Moons Explorer, intended to specifically study Ganymede, Callisto, and Europa, and the third is Europa Clipper, which is obviously intended to do close studies of Europa. However, these will have to be covered in more detail once they actually reach their destinations. For now, I think we'll end here. We've taken a glimpse into just how far into the stars humanity has reached, to every planet and out to the very edge of our solar system. Realistically, as far as we can go without developing some kind of faster-than-light travel, or using something like nuclear pulse propulsion. We tend to only think of Mars and Venus and the Moon, but really, we've done a lot of exploring of everything beyond as well. It's just that it's not exactly easy to land on a gas giant. Or, possible. By the way, thank you very much for watching, Tyson. I appreciate you.